Prepare to delve into the enigmatic depths of the universe, where an invisible force reigns supreme. In a cosmic dance between the known and the unknown, we bring you 10 facts on dark matter, a mind-bending journey that will shatter your preconceptions and ignite your curiosity. Brace yourself for a voyage into the mysterious realm of invisible matter, where gravity's secrets intertwine with the fabric of space and time. Get ready to question everything you thought you knew about the universe, as we unravel the enigma that has captivated scientists and astrophysicists for decades. Step into the shadows and unlock the secrets of the unseen. Dark matter awaits. Here are 10 facts about dark matter. 1. Dark doesn't just mean we don't see it. It means it doesn't emit any electromagnetic radiation, for all we can tell. Astronomers haven't been able to find either light visible or radiation in the radio range or X-ray regime, and not at even higher energies either. 2. Matter doesn't just mean it's stuff. What physicists classify as matter must behave like the matter we are made of, at least for what its motion in space and time is concerned. This means, in particular, dark matter dilutes when it spreads into a larger volume and causes the same gravitational attraction as ordinary, visible matter. It is easy to think up stuff that does not do this. Dark energy, for example, does not behave this way. 3. It's not going away. You will not wake up one day and hear physicists declare it's not there at all. Well, you will, but those claims are rare, and those physicists are wrong. The evidence is overwhelming. Weak gravitational lensing demonstrates that galaxies have a larger gravitational pull than visible matter can produce. Additional matter in galaxies is also necessary to explain why stars in the outer arms of galaxies orbit so quickly around the center. The observed temperature fluctuations in the cosmic microwave background can't be explained without dark matter, and the structures formed by galaxies wouldn't come out right without dark matter either. Even if all of this was explained by a modification of gravity rather than an unknown type of matter, it would still have to be possible to formulate this modification of gravity in a way that makes it look pretty much like a new type of matter. And we'd still call it dark matter. 4. Rubin wasn't the first to find evidence for dark matter. Though she was the first to recognize its relevance, a few decades before Vera Rubin noticed that stars rotate inexplicably fast around the centers of galaxies, Fritz Zwicky pointed out that a swarm of about 1,000 galaxies, which are bound together by gravity to the Coma cluster, also move too quickly. The velocity of the galaxies in a gravitational potential depends on the total mass in this potential, and the two large velocities indicated already that there was more mass than could be seen. However, it wasn't until Rubin collected her data that it became clear this isn't a peculiarity of the Coma cluster, but that dark matter must be present in almost all galaxies and galaxy clusters. 5. Dark matter doesn't interact much with itself or anything else. If it did, it would slow down and clump too much, and that wouldn't be in agreement with the data. A particularly vivid example comes from the Bullet cluster, which consists of two clusters of galaxies that have passed through each other. In the Bullet cluster, one can detect both the distribution of ordinary matter, most of the emission of X-rays, and the distribution of dark matter by gravitational lensing. The data demonstrates that the dark matter is dislocated from the visible matter. The dark matter parts of the clusters seem to have passed through each other almost undisturbed, whereas the visible matter was slowed down and its shape was noticeably distorted. 6. It's responsible for the structures in the universe. Since dark matter doesn't interact much with itself and other stuff, it's the first type of matter to settle down when the universe expands and the first to form structures under its gravitational pull. It is dark matter that seeds the filaments along which galaxies later form when visible matter falls into the gravitational potential created by the dark matter. If you look at some computer simulations of structure formation, what is shown is almost always the distribution of dark matter, not of visible matter. The visible matter falls into, and hence is assumed to follow the same distribution at later times. 7. It's probably not smoothly distributed. Dark matter doesn't only form filaments on supergalactic scales. It also isn't entirely smoothly distributed within galaxies. At least, that's what the best understood models say. Dark matter doesn't interact enough to form objects as dense as planets, but it does have halos of varying density that move around in galaxies. The dark matter density is generally larger towards the centers of galaxies. Since dark matter doesn't rotate with the disk of stars we observe, solar systems like our own constantly move into a wind of dark matter particles. 8. Physicists have lots of ideas about what dark matter could be. The presently most popular explanation for the puzzling observations is some kind of weakly interacting particle that doesn't interact with light. These particles have to be quite massive to form the observed structures, about as heavy as the heaviest particles we know already. If dark matter particles weren't heavy enough, they wouldn't clump sufficiently, which is why they are called WIMPs for weakly interacting massive particles. Another candidate is a particle called the action, which is very light but leaves behind some kind of condensate that fills the universe. Other types of candidate particles have more complex interactions or are heavier, such as WIMPsILlas and other exotic stuff. Macro dark matter is a type of dark matter that could be accommodated in the Standard Model. It consists of macroscopically heavy chunks of unknown types of nuclear matter. 9. And they know some things dark matter can't be. We know that dark matter can't be constituted by dim brown dwarfs or black holes. The main reason this doesn't work is that we know the total mass dark matter brings into our galaxy, and it's a lot, about 10 times as much as visible matter. If that amount of mass was made up of black holes, we should constantly see gravitational lensing events, but we don't. It also doesn't quite work with structure formation. And we know that neutrinos, even though weakly interacting, can't make up dark matter either because they are too light and they wouldn't clump strongly enough to see galaxy filaments. 10. But we have no direct experimental evidence. Despite decades of search, nobody has ever directly detected a dark matter particle, and the only evidence we have is still indirectly inferred from gravitational pull. Physicists have been looking for the rare interactions of proposed dark matter candidates in many Earth-based experiments starting already in the 1980s. They are also on the lookout for astrophysical evidence of dark matter, such as signals from the mutual annihilation of dark matter particles. There have been some intriguing findings, such as the PMELA positron excess, the DMMA annual modulation, or the Fermi gamma ray excess, but physicists haven't been able to link any of these convincingly to dark matter. As we draw the curtain on the enthralling exploration of 10 facts on dark matter, we are left spellbound by the enigma and allure of this elusive cosmic entity. Dark matter, with its mysterious nature and invisible presence, challenges our understanding of the universe and beckons us to venture into the depths of the unknown. Its gravitational influence shapes the cosmos on a grand scale, yet its true nature remains tantalizingly beyond our reach. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.